Okay. So we discovered before break, right, that exponential functions are very much related to our new logarithmic functions. Also recall that we have different types of logarithms, right? We have common log, which is really log base 10. This one right here, you see the little subscript of 2, right? So this is log base 2 of x. Okay, so we're going to graph these two functions, f of x equals 2 to the power of x, as well as g of x equals log base 2 of x on the same grid. Okay, so with all functions, right, the way you can graph them is you pick x values, plug them in, and get the y values, right? So, you know, the first numbers you probably think of are, okay, well, what about x is 1, 2, 3? Okay, so if you plug each of those into f of x first, 2 to the power of x becomes 2 to the power of 1, which is 2, right? So when x is 1, f of x becomes 2, so 1 comma 2. Right, then when x is 2, 2 to the power of x becomes 2 to the power of 2. 2 times the second 2 is 4, so 2 comma 4. Then when x is 3, 2 to the power of 3, 2 times 2 times 2 is 8. No, because it's a positive 2, yeah, equals. Thank you. Okay, but we also want to remember that exponents don't have to be positive numbers. We could also do x is 0, because 2 to the power of 0, right? This is just sort of like a property that's easiest to remember. Any other number to the power of 0 equals just 1, so 0 comma 1. And we also want to remember that exponents can be negative numbers as well. Right, so x equals negative 1 would mean that 2 to the power of negative 1 becomes 1 over 2 to the power of positive 1, which is just 1/2. Okay, so we could do negative 1 comma a half. Okay, and maybe I'll squeeze in one more point. I'll go back one more. X could be negative 2. So 2 to the power of x becomes 2 to the power of negative 2, which is 1 over 2 to the power of positive 2, which is 1/4. Okay, so negative 2 comma 1/4. So with those points, we can definitely see the shape of the graph. To the right, the graph is rapidly increasing, right? You can see the y values are going upward very quickly. Okay, we will draw an arrow on the end because they continue. And to the left, you can see that the graph is flattening out. Okay, so it'll never quite touch the x-axis because no matter how negative x is, it'll always be 1 over a number. So it'll always be bigger than 0 because the numerator is 1. Okay, so to the left, we want to flatten out our graph. Okay, but again, we do draw an arrow because you can go forever to the left. Okay, and I'll just label this was f of x, which is 2 to the power of x. All right, so that's the exponential function. Again, this one you've been working with for a couple of years at least, so this one should look very familiar. The one that we introduced here in Math 3 is the logarithmic function, log base 2 of x. Right, so here you don't really want to plug in x values one by one because most x values don't simplify nicely. The decimals go on forever. Okay, so we want to sort of similarly to what we did with square and cube root functions, we want to use the good x values, the ones that simplify nicely. Okay, so the key thing to remember about how logarithms work, 1 second please. Okay. We want to remember about logarithms, right? So when we calculate what does log base 2 of any number x equal, okay, what we, again, discovered a couple classes ago is that the logarithm tells you what exponent to put on the base to turn into the argument. Okay? So the equivalent equation to log base 2 of x equals some question mark. 2 to what exponent would turn into the argument x? Okay, so again, these two statements mean the exact same thing. Okay, so you want to be familiar with converting back and forth between them. Okay, so with that in mind, the good x values will be powers of 2, right? It'll be 2 to some unknown exponent. Okay, so I know that a power of 2 would be 8. Okay, so again, the calculation that I'm really doing here is I'm figuring out what does log base 2 of 8 equal. But if I rewrite this as an exponential equation, right, I'm asking what exponent do I put on this base of 2 to make it turn into the argument of 8. Okay, and so looking at it like this, I can recognize that, oh, it would have to be 3. 2 to the power of 3 would turn into 8. Okay, so when x is 8, y is 3. Oh, sorry, 3. Okay, let me do one more with you. I remember from earlier that 1/4 is a power of 2. Okay, so again, when I plug in 1/4 for x, right, so I'm figuring out what is log base 2 of 1/4. What does that equal? Again, the question is really, what exponent goes on that base of 2 to make it turn into the argument of 1/4? Okay, so I know that it has to be a negative number in order to turn into a fraction, and then to go from 2 to 4, you would need to have an exponent of 2. But again, we make it negative 2 because it's a fraction. Right, so log base 2 of 1/4 would be negative 2, because 2 to the power of negative 2 is how you get to 1/4. Okay, so we can also put a point at when x is 1/4, y is negative 2, so 1/4 comma negative 2. Sorry, I guess. Okay, so why don't you go ahead and see if you can do a few more points for log base 2 of x. All right, so again, strategize, think about the good x values. You really shouldn't need a calculator for this, right? If you understand what a logarithm does, you'll be able to come up with these numbers without needing any sort of calculator. Okay, go ahead and try it out for a couple minutes. Sure. Go ahead and try that and see what happens. To write it in general, but this point doesn't quite work for 0, 0, because log base 2 of a 0 would be asking 2 to what exponent equals 0, and we can see that, right, when the base is 2, it never quite equals 0. Okay, see if you can fix that point. Seems like a lot of you are making good progress. So again, you can just continue doing points one by one, right? You might also remember, oh, 4 is a power of 2. Right, so log base 2 of 4, that's asking 2 to what power turns into 4? It'd be 2 to the power of 2. All right, so you got 4 comma 2. Okay, but we can also look over here, right? Because these y values for the 2 to the power of x function, those are all powers of 2, right? So these are all good x values. And we actually don't really need to calculate the y values because we learned that 2 to the power of x and log base 2 of x are inverse functions, right? So we know that inverse functions, you just switch x and y. Okay, but again, thinking about it logically, where did 1/2 come from? 1/2 is the answer when you do 2 to the power of -1. So log base 2 of 1/2 is asking what was that exponent that created 1/2, right? That exponent was -1. Okay, so again, we're just switching x and y, really. Okay, so 1/4 -2 is already there, 1/2 -1, 1, 0, 2, 1. Okay, so looking at this graph, to the right, the graph is not flattening out. It is continuing to go upward, so there's no horizontal asymptote. But to the left, you can never use 0 itself, and you can never go negative. Okay, so we do approach a vertical asymptote on the left. Okay, so now that we all have the 2 graphs, see if you can remember this part. What do we do to map the first graph onto the second one, right? Like, how do you change this graph to make it land perfectly over here? Okay, and if you remember that, I kind of gave this away already. Yeah, you're right. Okay, so let's make sure we remember this first part, though. How do we map, for me, the red graph to land perfectly on the blue graph? What transformation, meaning what translation, reflection, or rotation would change one into the other? Does anyone think they see the correct action? Let's give Joey a chance. Okay, reflecting over y equals x. So y equals x is the diagonal line that goes from the bottom left to the top right through the origin. So yes, if you reflect this point, it'll flip over here, this point goes here, this point goes here, and so on. Okay, so yes, you reflect over the line y equals x. Okay. And then we saw this back in Unit 3, but we know that when this is the case, when 2 functions are reflections over y equals x, that means that they are inverse functions of each other. Yeah, that's fine. That says log base 2 of x and 2 to the power x are inverses of each other. Okay, so yeah, that was just a little warm-up and review of what logarithms do and their relationship to inverse functions. Okay, so we're also going to tie this into a new concept. Okay, so we're going to look at how to sort of combine functions together. So to understand this, we're going to just do a little simple scenario. Okay, so there's two people, Adam and Bob, who work at the same place. They earn the same salary. So let's just make the numbers easy. Let's say that they each earn $10 per hour that they work. Okay, so if they work for X hours, how would you calculate the total amount of money earned? Yeah, you would multiply 10 by the number of hours X. So 10 times X is just 10X. Okay, so Adam, who worked 3 hours, you substitute 3 in for X. 10 times 3, he earned $30 total. And Bob worked 8 hours, so again, his X is 8, so 10 times 8 is 80. Okay, so that's just a one-step linear function. Right, this is nothing new, but we're going to build on this. Okay, so now let's say that these two people like buying packs of baseball cards. So let's say that they cost $2 each. Okay, so forget about the top function for a second. Okay, ignore those numbers. Okay, so if you have X dollars, what calculation tells you the number of baseball card packs you can buy? All right, what would you do to X to solve for the number of baseball card packs? Okay, go ahead, Joey. Yeah, every pack costs $2, so you would divide X by 2. Okay, so now we will go ahead and bring back the first couple numbers. So remember, Adam had $30 earned from working. So in order to calculate his number of baseball card packs, you would take that 30 and divide it by 2. Correct? Okay, so similarly, Bob, he worked more, so he has $80 to spend. But every pack still costs $2. So you take his amount of money, divide it by the $2 per, and he can afford 40 packs of baseball cards. Okay, so now just summarizing, Adam worked 3 hours, and that was enough to buy 15 packs of baseball cards. Bob worked 8 hours, and that was enough to buy 40 packs. Okay, so we did this in 2 steps, right? We took the number of hours, we calculated the dollars, then we took the dollars and calculated the number of packs of baseball cards. Okay, so again, we did 2 calculations, hours to dollars, dollars to packs. Okay, but there's probably a shortcut, right? A way to do it in 1 step, right? So if you ignore what we did above and just focus on this last table, Adam worked 3 hours, and he was able to buy 15 packs of baseball cards. Bob worked 8 hours. He was able to afford 40 packs of baseball cards. Okay, so instead of doing 2 separate calculations, there's a way we could have done it with just a single calculation. Okay, so this is not a trick question. This is as straightforward as it looks. Right? What is the shortcut that we can, what do we do to the number of hours to go straight to the number of packs of baseball cards? Go.
Multiply by 5.
Okay, yeah. 3 times 5 is 15, 8 times 5 is 40. Okay, so oh, sorry. Yeah, it takes a second for it to focus, I guess. Okay, so yeah, 3 times 5 is 15, 8 times 5 is 40. So instead of doing a 2-step calculation, we can now do it in just 1 step. Thank you. Okay, So yeah, just to illustrate this, let's pretend there was a third person, Carla, ABC. Okay, and she works the most out of anyone. She works 12 hours. Okay, so again, if we do it the two-step way, first we would do, okay, she works 12 hours at $10 each, 12 times 10, she earns $120. And then, now that we know that she earned $120, we would divide that by $2 per pack. Yep. Okay, but according to what we discovered, I just want to do one more example. Okay, so instead of doing it the long way, right, we could have just done the new shortcut. We could have taken the number for hours times 5. 12 times 5 is 60. Okay, and so you see, we do end up with the same answer. Okay, so yeah, I'm sure you guys see the benefit of combining the two functions, right? Instead of doing two calculations, you can do one calculation and get to the same answer. Okay, so this concept of combining more than one function together, this is called a composition. Okay, so you've probably heard the word composition outside of math, like in music, right? A composition is like multiple instruments playing. Yeah, composite is another related word. Okay, so let's show why this shortcut always works, right? It works for all three people. Okay, so our very first function was m of x equals 10x, so let's rewrite that. Oh, sorry, should not have an extra line there. Okay, and then the second function, n of x equals x over 2. Okay, but the way the situation worked was we took the answer to the first function and we used it as the input for the second function, right? So we took this output and made it the new function's input. Okay, so if we look down here, for the second function, we wouldn't use x anymore, right? We would take the first function's output and use that as the second function's input. Okay, so instead of doing n of x, we're really doing n of 10x. Okay, so that means instead of x over 2, because the input is 10x, it would be 10x over 2. Okay, and we can see that 10x divided by 2 simplifies to 5x. Okay, so this is a composition, right? We took the two separate functions and we combined them together into a single function. Okay, so yeah, compositions can be beneficial because they can save us time, right? Instead of doing two different things, we can go straight to the answer by using the composition instead. Okay, so any questions about this, well, the entire front page? Okay, let's go ahead and turn to the second page then. Yeah. Yeah, that's right. Yes. Yeah, probably. That's still being finalized. Okay. So on the second page, we can now tie together the two concepts from the front page. We can prove that two functions are inverses by performing a composition. Okay, so this is a separate skill, a separate learning target from the Unit 3 inverses. Okay, so please be aware you do need to show your work this new way that we're going to go over together right now. Okay, so here's two functions. A of x equals 2x plus 5, and b of x equals negative 7x plus 5. Okay, so two brand new functions. Down here, we see sort of a crazy looking thing with a lot of parentheses, right? So you would say this out loud as a of b of x Okay, just so you're aware, sometimes you'll also see it written like this. So parentheses, A, and then like a floating O, B, close parentheses of X. Okay, so yeah, these mean the same thing. So just be aware. Okay, so how do you do this? Well, it's actually pretty much what we did on the front page, right? If I show you this again for a second. We calculated the inside first, and then we took that answer and we plugged it into the second function. Okay, so to calculate A of B of some number, we would first calculate the inside and then take that answer and plug it into the outer function. Okay, so to make it make more sense, let's jump into a number. Let's say that we want x to be, let's just do, let's do negative 2. Okay, so how do we calculate this A of B of, in this case, x is negative 2. Okay, so A of B of, but then again, x is going to be negative 2 here. Okay, so you just work from the inside out. Okay, so you're going to keep the big A parentheses for now, which for me is in blue. Sorry, that's an A, not a 9. Okay, so again, just leave that A there, but then now calculate B of negative 2 on the inside. Okay, so if we look back up here, right, that's the function that B is. Okay, so let me color code this a little bit. Okay, so again, the inner function is B of negative 2. So ignore A, pretend that the A is not even there. Just pretend I asked you, what is B of negative 2? Okay, so going back over here, we would plug negative 2 in for the x, right? So keep the negative 7, but x is getting replaced with negative 2. And then after the negative 7x part, we have a plus 5. Okay, so again, keep that outer A, but now take the inside and simplify. Okay, negative 7 times negative 2 would be positive 14, plus 5 would be positive 19. Sorry, my 8's keep looking like 9's. Okay, so now that we've done the inner part, now we can do a of 19 like normal. Okay, so now we look at the a function. Okay, so 2x plus 5. All right, so you keep the 2, you keep the plus 5 at the end, but then x is now 19. Okay, so 2 times 19 would be 38, plus 5 would be 43. Okay, so yeah, when x is negative 2, a of b of negative 2 simplifies down to 43. Okay, so let's have you guys try it for a second. So I didn't really plan the space well here, but go ahead and try to calculate wherever you have room. A of b of negative 1. All right, everyone. Let's go ahead and see if you were able to do this correctly. Okay, so again, you work from the inside out, so leave the a for now, but calculate b of negative 1 using the b function. Okay, so negative 7x plus 5 becomes negative 7 times negative 1 plus 5. Okay, so simplifying that inside part, negative 7 times negative 1 is positive 7, plus 5 is 12. Okay. So now we take that answer and we use it as the input for the outer function a. Okay, so now we look over here. So 2x plus 5 becomes 2 times 12 plus 5, which would be 24 plus 5 is 29. All right. So with that in mind, let's go ahead and now take a look to the right. Okay, so here we have b of a of x. Okay, so it's the same two functions as before, but does the order matter? Right? We know in math sometimes the order matters, sometimes it doesn't. Right? When you add, addition is commutative. 5 plus 8 and 8 plus 5 are both 13. Right? But when you subtract, the order matters. 5 minus 8 is negative 3, 8 minus 5 is positive 3. Okay, so let's go ahead and test it out. Let's calculate b of a of negative 2. Okay, so earlier we did a of b of negative 2, right? So now we're doing b of a of negative 2. So we want to see if we get the same answer. We want to see if we end up with 43 again. Okay, so just like before, the way you do this, you do the outer function first. Or sorry, you leave the outer function alone. So I said that backwards. Okay, so leave the b function where it is. But now let's do the inner function. Okay, so a of negative 2, you look at the a function. A is 2x plus 5. So keep the 2, keep the plus 5, but then 2x becomes 2 times negative 2. Okay, 2 times negative 2 is negative 4, plus 5 would be positive 1. Okay, so the inner part simplifies to 1. And then now we do b of 1. Okay, so now we look at the b function. B of x was negative 7x plus 5. Oh, sorry. Okay, so again, negative 7x plus 5, but x is now positive 1. Okay, negative 7 times 1 is negative 7, plus 5 would be negative 2. Okay, so we see that from over here, a of b of negative 2 equaled 43. Okay, but then we saw from here that b of a of negative 2 equaled negative 2. Okay, so that must mean that the order does matter with composition. Right? We did the same two functions, we used the same x value, but we got two different y values. Okay, so before we continue, let me see if there's questions about what we've done so far. Okay, so now look how much space one problem took, right? We had to write a whole bunch of things. So just like we saw with the baseball cards, let's try to do a composition of functions. Okay, so let's go back to the first order, a of b of x. Okay, so again, a for me is blue, and then b of x is red. This is what we did earlier, a of b of x. Okay, but this time we're going to leave the x as x. We're not going to plug in a specific number. Okay, so what we want to do is, for the outer function, well, we can write it like this. So 2x plus 5, right? So 2 times whatever x is plus 5. right? But this time, instead of x being x, the input is b of x. Okay, so in this parentheses, you're going to substitute b of x, okay, the entire function. Okay, so now we just simplify. Okay, so we have a 2 that's multiplying this parentheses, so it gets distributed out. 2 times negative 7x would be negative 14x. 2 times positive 5 would be plus 10. Okay, and then this other plus 5 is outside the parentheses, so it's not affected by the 2, but it is still there. Okay, and then negative 14x, you combine these two, right? Plus 10x plus another 5x combines to plus 15x. Sorry, plus 15. Okay, so according to this, we can do the composition a of b of x by instead doing negative 14x plus 15. Okay, so let's verify that this works. Okay, so earlier we did a of b of negative 2, right? And we did like a long 2-step calculation to get an answer of 43. Let's see if we get the same answer with this composition. Okay, so again, we don't need to look at the individual parts anymore. We look at the composition. Okay, so substituting negative 2 into the composition, negative 14x becomes negative 14 times negative 2 plus 15. Negative 14 times negative 2 is positive 28. 28 plus 15 is 43. And that is the same answer as earlier. Okay, and let's verify one more time. We also separately calculated over here that a of b of negative 1 simplifies to 29. Okay, let's see if the same thing happens with the composition. Okay, so again, using the composed function, negative 14x becomes negative 14 times negative 1, and then you have a plus 15 at the end. Negative 14 times negative 1 is 14, plus 15 is 29, right? And that was the correct number from earlier. Okay, so again, you can see how much faster it is with the composition than with the two individual functions. Okay, so I'd like you to try finding the composition b of a of x. Okay, so, same idea that we did over here, but the order is different. B is on the outside, a is on the inside. Okay, so go ahead and try this out for a minute, please. Table down below, trying to do the same thing for b of a of x. Okay, so what you should have done here for b of a of x, right? You take the outer function, in this case b, and you copy it down, except you replace the x with a big parentheses. Okay, because again, the input is not simply x, it's the entire output a of x. Okay, so in that parentheses, you copy the a of x function. Okay. And now we can go ahead and simplify. Negative 7 times 2x is negative 14x. Negative 7 times positive 5 is negative 35. And then you still have a plus 5 at the end. Okay, so simplifying, we get b of a of x is negative 14x minus 30. Okay, and again, let's check it by using the value from earlier. When x is negative 2, y should also be negative 2. Okay, so let's try substituting that x into the composition. Negative 14 times negative 2 is positive 28. 28 minus 30 is indeed negative 2. Okay, so this composition is correct. Okay, so those two functions, 2x plus 5 and negative 7x plus 5, right, if we were to graph them, they would look something like this, right? 2x plus 5 would look kind of like this, and then negative 7x plus 5 would be very steep, but pointing the other direction. Okay, so these two functions are not inverses, right? They are not reflections over y equals x. Okay, but now let's look at two brand new functions. Okay, c of x equals, in the numerator, negative 16 plus x all over 4, and d of x equals 4x plus 16. Okay, so in a previous worksheet, we found that these are inverses. Okay, if you graph them, they are reflections over y equals x. Okay, so I would like you to again practice what you did up here. Right, I want you to do the composition of the two functions and go ahead and do it in both orders. Right, so first have c on the outside, and then after you've simplified as much as possible, put function d on the outside. Okay, so please take a couple minutes and try to do these two compositions. Again, you're leaving x in the function, you're not picking a number for x. So remember, you're inputting this for x, so everything else stays. So you should copy this down, but replace the x with this here. Right. Okay, I'm going to simplify that as much as possible. Because the negative 16 doesn't multiply here because there's a plus sign between them, so it doesn't touch it. times the entire numerator. So you should combine up the numerator first and then divide afterwards. Yes, keep going. Yeah. Yep, gonna try the other one. Yeah. Right, you would not distribute the plus sign. So in this case, the parentheses actually don't equal because there's no coefficient of x. Okay. So if you think about the reason that logically that makes sense.
They're inverses of each other.
Right. So why does it equal x make sense for inverses?
Because they don't intersect.
The inverses
But
could
they
intersect.
can intersect. Okay.
So think about, remember, inverses undo the action
They
of each
undo
other,
it.
right?
Each undoes the action of the other.
That's true. So the x gets replaced by this. So that first x is not here. Because when you put this in, the original x is gone. All right, let me go ahead and go through this. Okay. So for c of d of x, the outer function is c. Okay. So I'm going to copy c of x down, but I'll replace the x with big parentheses. Right, because again, we need to input the other function in for x. So in that parentheses, I will input d of x, which is 4x plus 16. Okay, so now in this case, the parentheses don't actually have an effect. There's no coefficient. The negative 16 doesn't multiply because there's a plus sign between them. Again, no coefficient, no exponent. So the parentheses can actually just go away. And then from there, you can either combine up the numerator first, or you can divide. I'm going to combine the numerator first. So negative 16 plus 16, those cancel out to 0, right? So that just leaves 4x over 4. And 4x divided by 4 would be just x. Okay, so c of d of x simplifies to just x. Okay, and now let's do the other order, d of c of x. So this time the outer function is d of x. Okay, so 4x plus 16, I replace the x with a big parentheses, but keep the 4 in front, keep the plus 16 at the end. And in that parentheses goes the inner function. Okay, so we've got 4 times the quantity, negative 16 plus x over 4, and then all of that plus 16 at the end. Okay, so there's a couple different ways you can do this, but probably the most straightforward is if you turn the 4 on the outside into the fraction 4 over 1. Now, because these are multiplying, we can reduce the common factor of 4. All right, some of you may have heard this called like cross-canceling. All right, so you can reduce the 4s. So now you just have the negative 16 plus x from here, and then you still have the plus 16 at the end. Okay, but negative 16 plus 16 is 0. Okay, so that just leaves the x behind. Okay, so that means that d of c of x also equals x. Okay, so yeah, both orders, the composition simplified all the way down to x. Okay, so in order to help understand what happened, let's do a specific number. Okay, so I'll just do negative 2 again since. Okay, so c of d of negative 2. Let's do the inside separately. Okay, so what color? Blue. Okay, so we know that first we would do the inside, right? We would do d of negative 2. Okay. Again, I'm just inputting the chosen x value into the given function, d of x equals 4x plus 16. Yeah, like with many things, when you first see a topic, it is trickier, but as you get more practice, you'll get more familiar with it. Okay, so yeah, the output of d of x is 8, right? So in order to do c of d of negative 2, okay, so we've already calculated the outside, right? I'm sorry, I said that backwards. We've already calculated the inside. I already know that d of negative 2 becomes positive 8. Okay, so now let's go ahead and calculate the outer function, c of positive 8. So substitute positive 8 into c of x up here. Okay, negative 16 plus x over 4 becomes negative 16 plus 8 over 4. Negative 16 plus 8 is negative 8 over 4 is negative 2. Okay, so let's think about this. We started with negative 2. D of x changed that negative 2 into an 8, but then c of x took that 8 and gave you back negative 2. Okay, so remember, that's like the definition of an inverse function. We said an inverse function undoes the action. So again, d of x changed negative 2 into 8. C of x undid that and turned the 8 back into the starting negative 2. Okay, so yeah, it's not a coincidence that these two inverse functions had a composition that simplified to x, because that's what an inverse does, right? Whatever you start with, the original original function changes it, but the inverse changes it back. So since you started with x, you should end with x after a composition. Okay, so it's not just that the two functions ended up at the same thing. They always will specifically end up at simply x, right? Because x is the input, so x has to be the output of a composition of inverses. Okay, so why don't we go ahead and write that below. Okay, so the composition of two functions that are inverses will always simplify to x. Okay, and I'll add this is true in both orders. As we saw above, whether we do c of d of x or d of c of x, the composition of two functions that are inverses will always simplify to simply x. Okay, we're going to add one more sentence here. Okay, so what happens if you do a composition of two functions and it does not simplify to x? That means that they are not inverses. Okay, so this is how we'll be checking if functions are inverses or not. We do the composition of them. If the functions simplify to x in both orders, that means that, yes, they are inverses. But if the composition leads to anything except for x, that means that the two functions were not inverses. Okay, so again, this is a separate learning target from Unit 3. So in Unit 3, the way we found inverses was we switched x and y and we found the new y. That is not what we're practicing in Unit 4. Okay, so you have to use the strategy of compositions in order to earn credit for this learning target. Let's go ahead and turn to the third page now. Okay, so instructions. Determine if the following two functions are inverses, and get the key part through compositions. Okay, so do not switch x and y. That's not our current learning target. We're going to use compositions to do this. Okay. So I'm going to have you guys try it out. Why don't you try the first two pairs? Right. So for question 1, take m of x and n of x, do a composition, and see if that means the two functions are inverses or not, and do the same thing for the pair in question 2. Yeah. By the way, to prove something's a composition, you want to check both orders. But if the first composition fails, you don't need to check the second one. So it has to work twice to say yes, they're compositions, but it only has to fail once to say no, it's not. Sorry, not an inverse. So, yes. So I think you are getting, you're thinking of square roots, right? Square root. Square root x to the square root x squared plus or minus x. But this is a cube root. The sign stays the same. Sometimes you get, most of the time it's fine, but sometimes you get a lucky and they just happen to match the actual number. So you want to keep the x. How do you combine them? So like this.
That's me. I can tell that I was like level in English. 6 or 6.5. I can't use 6.5. No, it's okay. Let's work on this and we can get your grades up. I'll just ask her if I can use it.
Okay. So when you do a composition, you're not doing like inverse operations or anything. You're just doing the operations that are written there. So like, how do we simplify this? Like, what do we apply to what operations?
That's where it feels important.
Finish the first two, you're welcome to continue on to the other columns on this page.
So these are inversions of each other.
And the other way. Okay. So the way you input it is correct. And then like before, the parentheses have nothing, they have no effect. There's nothing in front, there's nothing behind, so you just drop the parentheses, and then now you can try to simplify it. not solving for x. You're just like we did over here, right? Like when you take two functions, you combine them together. The answer is not always going to be simply x. Right? That's what we want to understand from here. So here, both directions simplify to x. So the conclusion is these two functions are inverses of each other. But as you saw here, when you combine these, they do not simplify to just x. So there's no way to solve for x. You just conclude, oh, because it's not x, that means that these were not inverses. Okay, so for problem 1, I'll do m of n of x first. The order doesn't really matter. Okay, so for me, m of x is the outer function. So 2x cubed plus 3 becomes 2 parentheses cubed plus 3. And then we will fill in that parentheses with the other function. And now we simplify. So order of operations, parentheses comes first, but there's nothing to do in the parentheses. So next comes exponent. We have a power of 3, which cancels out the cube root, the index of 3. Right? So the radical and the cube cancel out. So now you have 2 times quantity x minus 3 over 2, and then plus 3 at the end. Again, if we change 2 into 2 over 1, we can now see that the common factors of 2 can be reduced. So then x minus 3 plus 3 does become simply x. Okay, so you can't stop here and say, yes, they're inverses. It is possible for one way to say x, the other to not, and in that case, it would not be inverses. Okay, so you do need to do both directions to prove that things are inverses. Okay, so let's go ahead and try the other direction, which for me is n of m of x. Correct. Yes. Okay, so this time I will replace the x over here with a big parentheses and fill in that parentheses with the other function, 2x cubed plus 3. Okay, so these parentheses don't actually have any effect. There's no coefficient, there's no exponent on the parentheses, so the parentheses just go away. So that means the plus 3 minus 3 cancels out, leaving 2x cubed over 2 on the inside. Okay, but now the 2's can cancel out, leaving you with cube root of x cubed, and the cube root of x cubed is just x. Okay, so once you have verified that both orders of composition simplify down to simply x, you are able to conclude that they are inverses. Okay, so yeah, make sure you write your conclusion. Okay, yeah, if you just show the work and you don't tell me what it means, that isn't going to be able to earn you credit. You have to show your understanding that, oh, when both orders lead to x, that means that, yes, they are inverses. Okay, the next pair, r of x and s of x. Again, you can do either order. I'll just do r of s of x. Okay, so I'll keep the r of x as 4 minus 3 over 2, but instead of x, we replace the x with the other function. Okay, I'll keep the 4 on the outside. And distribute negative 3/2 times 1/2 x would be negative 3/4 x. Negative 3/2 times positive 3/2 would be minus 9/4. 4 is equal to 4 over 1, which is equal to 36 over 4. Okay, so this becomes negative 3/4 x. Sorry, not 36. Where did I get that from? Sorry, that should be 16. Okay, but still, 16/4 minus 9/4 would be positive 7/4. Okay, so this is not simply x, right? It's negative 3/4 x plus 7/4. Okay, so you don't need to bother checking the other direction because both have to work to be inverses. So if even one does not work, that means they are not inverses.
If one does work, you still have to check the other one.
Correct. So last thing we'll do, this question over here. Okay, so the warm-up from today, right, we had 2 to the power of x and log base 2 of x. Okay, so this is going to look kind of crazy. What does g of f of x look like? Okay, so g of x is log base 2 of x, and f of x is 2 to the power of x. Okay, so we need to try to simplify this. Okay, so it seems kind of impossible, right? Like, how are we supposed to know what this equals? But if we think about it with regular numbers, it's actually pretty straightforward, right? Because again, let me do a little side problem. Right, when we do log base 2 of 8, right, because the real question is 2 to what exponent equals 8? Okay, so let's do that exact same thing over here. Right, so the base is the red 2, and a logarithm means we're figuring out what exponent to put on that base of 2 in order to equal the argument. Okay, so in this example, the argument was 8, so we made it equal to 8. In this example, the argument is 2 to the power of x, so we set it equal to 2 to the power of x. Okay, so when you rewrite the logarithm as an exponential equation, now it's kind of a silly question, right? It's 2 to what exponent equals 2 to the power of x. Well, the 2 matches, right? So the question mark has to be x. Okay, so we just figured out that log base 2 of 2 to the power of x equals simply x. Okay, so it does simplify down to just x. Now, the other order is more complicated. Sorry, wrong color. Okay, so f of x is 2 to the power of, and then g of x is log base 2 of x. Okay, so yeah, this one's a little bit trickier to understand. We won't get into right now, but because these are inverses, this will also simplify down to simply x. Okay, so yeah, this will be important to remember later in the unit, right? This property and this property, those will be very useful. Okay, so those of you who look at your assignment sheet, you may see that the homework tonight, rather than an exit ticket, it yeah.
It's a quiz.
Yeah, so like always, the quiz does not directly affect your class grade, but
That's all how to test right?
yeah. And then your homework is corrections. So the better you do the first time, the less homework you'll have. So the quiz is actually on Delta Math, but I also printed it out so that you can do your work on paper.
Is the quiz homework?
We have less than a minute.
Oh, no. Girl, I did not. Yeah, I was
We have less than a minute, though.
Yeah, this is for homework.
赶紧睡一个好觉。安吉啊。I wrote that starting careless and I want to try myself.
Okay, so again, don't bring the hard copy next class. You have to type